Hi, I'm Elizabeth, and I'm going to be talking about Lab 3, the magnetic field of a bar magnet. So a quick overview of what I'm going to be talking about. I'm going to start with the introduction, where I talk about our fundamental principles, an introduction to the lab, observations, and some of the procedures. And then I will talk about experimental data from my Excel spreadsheet for my measurements and some hand calculations that I did. And then I'm going to go in and talk about the code, show my glow script model, output, and visuals, and then talk about the results. So comparing and contrasting the hand calculations and code output, and then I go into a conclusion where I'm going to answer the what if and why questions and add some concluding remarks. So starting off, the fundamental principles used, we used the Biot-Savart law, superposition of magnetic fields, the magnetic field of a dipole on axis, and linearization. And then here are some of the formulas that we used. And then a quick introduction to the lab. We are going to measure the distance dependence of magnetic fields using a small bar magnet and compare against the Biot-Savart law predictions. And then I'm going to utilize a magnetometer app to accurately measure the magnetic fields. And then the system of this experiment is the bar magnet, and the surroundings would be everything else around that. So some observations I had: when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. Yes, I found that to be true. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. No, I found that actually it increased. And the position of the magnetometer has no effect on the measured x component of the magnetic field. No, that is not true. And like I said, the last one I found to be true. So part one of the procedure was finding the magnetometer chip, and I did this by sliding the phone perpendicular to the ruler in order to until I maximized the bx and minimized the by, and then I marked that position with the tape, rotated the phone 90 degrees, and repeated the process. And then for part two of the procedure, I was trying to measure the magnetic field. I zeroed the bx component before measurement, and I wanted to find the horizontal distance where the net magnetic field magnitude B net reached 100 microteslas. And then I recorded the By component at that distance, and then I vertically moved the phone, recorded all components, and repeated the process. So here's some of the experimental data that my phone measured in an Excel spreadsheet. And then I was actually able to use this data and the slope of the line ln bx versus ln r to do some hand calculations. I found that the slope was the same as one of the formulas from above, and I could use those values to calculate k, and then I could use the Biot-Savart law, set the magnetic fields equal to each other, and solve for mu, which I found to be 2.7 a times meter squared. And then going back to my Excel spreadsheet, I found that the distance was 0.2232 meters, and the average magnetic field at 45 degrees is 6.355577 times 10 to the negative 5 Teslas. And then here's some of my glow script code where I created a function for dipole B with mu and r, and then I was creating some arrows. And then here's the rest of the code where I created more arrows and was creating my visual. And so here's my output where I found that D is equal to 0.2347 and the magnetic field at distance D. And then here was some nice representation of that. So then comparing my results, I found that both from the calculations and the code that D was approximately 0.23 meters, which is good. And then for the magnetic field, the code gave me 3.299 times 10 to the negative 5 Teslas for the magnetic field magnitude. But the calculations gave me 6.355 times 10 to the negative 5 Teslas, which is about a 90% difference. So then what if I hadn't oriented the experiment to compensate for magnetic north and had instead just laid the meters stick out at some other position? So when we orient it at magnetic north, it zeroes out the x component, and if I didn't do that, the x component of my results would obviously change. And then what if I were to stick two identical magnets together end to end and run the experiment again? This would cause the measurements to be different because our magnetic field would increase. And then in conclusion, we can use bar magnets to accurately model magnetic dipoles, and as the magnetometer moves closer and farther away from the magnet, it changes the x component. And we can model this using experimental values and hand calculations. And some sources of potential error was that there could be electrical equipment nearby my experiment, failing to align my phone with the north before starting, or having steel or iron objects near the smartphone would affect the measurements. And that's it. Thank you for watching.